Okay, thank you very much for the invitation. It's great to be here and see many familiar faces and also some new faces in the field. So I'll be talking today about Cryo-Electron microscopy and in particular autocorrelation analysis to solve CryoEM. And so you may wonder, how does this relate to distant geometry? So perhaps many of you here have not heard about CryoEM. So CryoEM is a method for finding three-dimensional structures of molecules. So it's just like many of you perhaps heard about NMR spectroscopy as a method to determine three-dimensional structures at atomic scale resolution. Also CryoEM, cryo-electron microscopy, is a method for the same purpose, different type of molecules that we'll discuss later. And so you know that in NMR you get distances between atoms and maybe some other geometric information, and this allows you to build the molecule. But from the mathematical perspective, at the end of the day, what is distant geometry is all about is about solving a very large, perhaps, system of low-dimensional polynomials. So with distant geometry, if you just look at distances, these are polynomials of degree 2, and we get a long list of them, maybe with some additional constraints, maybe some additional maybe geometry, and then we need to solve the problem. So it should not come as a complete surprise that for a different technique in structural biology, where the goal is also to find the three-dimensional structure, I will show you today a mathematical formulation of the problem that leads also to a system of low-degree polynomial equations, and it's a large system that we'll need to solve. Okay, so that's like a long introduction to the talk, just so you to keep in mind where we are heading, okay? Because it's going to be a bumpy road to get to that to get to the stage. Okay, and I'm not even going to start with CryoEM. So just to get us started, I'm going to talk about a problem that sometimes we call it multi-target detection. But basically, the problem is in front of your eyes. So on the left, you see 4 planted images of Einstein. And if I would ask you, OK, now estimate what is the underlying image. OK, so you just pick one, and you say, OK, just declare one of them to be the estimated image. In the middle, you see the same picture, but with a little bit of added Gaussian white noise to it. And now if I'll ask you, OK, estimate the underlying image. So you say, oh, if I'll just pick one of them, maybe it will be too noisy. What I should do is to pick all 4 of them. I can still pick the images with our eyes, OK, and average those. And after averaging, I'll boost the signal-to-noise ratio, and this will be the estimation. But then on the right, the noise level is so high that none of you here can actually crop the images and select them in this very high level of noise. And then if I ask you, OK, now can you estimate the image? Maybe you look at me as I'm being crazy. OK, how can we do it if I cannot even find the particles in this high level of noise? So the first thing that I want to convince you is that even at such high noise levels, OK, where what is called particle picking, particle selection, or image selection is impossible, we can still reconstruct the underlying planted image. And the reason why we can do it is because it appears many times. Okay, so obviously, we're not going to do it from just one micrograph, just one big image like I'm showing you here on the right, but for many, many, many noisy micrographs. And in every such micrograph, there are, let's say, a few images of Einstein, but in every micrograph, maybe at different locations, not like in the first one. And because there is this repetitive signal that appears in all these micrographs, perhaps there is a way to do it. And I'm going to show you now that actually there is a very simple way to do it. OK? So by the way, this is such a high noise level that even if you knew the image, let's say Leo is an oracle, and he knows that it's an image of Einstein, if you will try to just find the picture inside, you will not be able to do it, okay? Because the correlation will be too stochastic. There will be too.
I couldn't find it.
Yeah, okay. Yeah, question.
You said it's because the image is repeated. Can we have sometimes maybe like similar images instead of like the exact same image, or is that not going to work?
Okay, so we'll see later on that in the real problem it's going to be actually much more complicated. Okay, so it's actually going to be the same molecule but viewed from different directions. So images are going to be actually quite different. Other questions? Yeah, please interrupt me anytime you like, okay? We are all friends, okay? So, okay, so, and I don't need to get to slide 29. Okay, so what's the secret? How we can do it? So the secret was in the title, autocorrelation analysis. So the first thing that you can do is just to estimate the mean pixel value. Okay, so this is just very little information about the image, but obviously you can do it. You can take all the pixels in the image, okay, and sum them up. And what are you going to get by averaging all of them? You're going to get the average value of noise, which is hopefully 0, okay, and the average value of the pixels in the actual image of Einstein. So you see that, okay, so if let's say I know the proportion of how many pixels belong to Einstein, how many belong to noise, I can actually estimate this very little information, the mean pixel value. Okay, that's very little, but you see that what helps us to do it is that I showed you some statistics, the average, and why did it work? Because it's independent of the actual locations. It's shift invariant or translation invariant. So let's now look for another such invariant. And what we'll compute is the autocorrelation. So what is autocorrelation? Now I'll take 2 pixels, not just one. I'll multiply their values, okay, and I'll scroll over the image, always keeping the displacement vector between them fixed. Okay, so I'm taking pixel x1, pixel x2, such that the difference x2 minus x1 is fixed, and I'm going through my image. Okay, so now I'll get autocorrelation, and I can play this game for any displacement. So what is this autocorrelation? This autocorrelation now has maybe 3 contributions. One is whenever I take 2 pixels inside the image of Einstein. So this will be the autocorrelation of Einstein with itself. I'll have the autocorrelation of noise with itself, and I'll have autocorrelation with Einstein with noise. Now, suppose that it's white Gaussian noise, so I know what is the autocorrelation of white Gaussian noise. The autocorrelation of Einstein with noise will average out to 0, and I'll end up with the autocorrelation of Einstein with itself. So I showed that I can estimate now the autocorrelation function of the image with itself. So, and this is great because, for example, I can take now the Fourier transform. This will give me the power spectrum of the image. And we know that in 2 dimensions, phase retrieval has a unique solution. Okay, so if I know the compact support of the Einstein image, I can solve the problem. So here are reconstructions. Okay, so these are reconstructions from the very, very noisy micrographs that you've seen on the right. But we use many, many, many micrographs. Okay. And you can see that for a large enough number of micrographs, we can get actually a really good solution. And here we just need to go to autocorrelations of order 2 to do that, because we rely on the fact that phase retrieval has a unique solution in 2D. So that is really nice because it already shows that no matter how poor is the SNR, the signal-to-noise ratio, with enough images, we can solve the problem. And if you think about it, what are autocorrelations? They're just polynomials of degree 2. Okay? In this case, there was some magic because we can solve another problem called phase retrieval problem. But in general, we'll need to solve some nonlinear inverse problem. Okay, so in general, we have these autocorrelations, okay? And I can define autocorrelations of degree of order 1, autocorrelations of order 2, autocorrelations of order 3. And I can do it over any array of numbers, okay? So I can do it for one-dimensional signals, so D will be 1. I can do it for images where D equals to 2. I can do it maybe even for volumetric arrays and so on. So, and the really nice, and it all works well because these autocorrelations are invariant to the actual positioning, okay? That's the trick. And there is another additional advantage of using autocorrelation analysis is that it requires just one pass over the data. So you see later on that in CryoEM, especially with, say, small molecules, we may need lots and lots and lots of images. So it's really like what's called a big data problem. And autocorrelation analysis allows you to solve this problem by just one pass over the data. You only need to gather the statistics, okay, the first stage. And then there is a second stage where we need to solve some nonlinear inverse problem, to go from the statistics and to estimate what is done on an object, like the image or the 3D structure, yeah.
Do you actually need to go over the whole picture, or can you maybe just sketch it and take a few random samples here and there?
I mean, if we don't have any prior assumption where are the images, then you can do sketching, but then you just need more data. I mean, if you have some prior.
Suppose you have so much data, so many data that you can't actually do a linear pass.
Yes,
You can sketch
so
it,
yeah,
you can still do it,
then
right?
just discard some of it, yeah. Right.
Is this in some sense identifying outliers? Is that some way of saying it?
What do you mean by identify outliers?
Well, if you got data and you know, and there's certain measurements that are, I mean, the pictures of Einstein are very different than the white noise.
But you cannot
In some
see
sense,
them.
they're outliers. Well,
May I just say, so the crucial issue is here, that noise, we know everything about noise, like we know that the average is zero, we know the autocorrelation. So the outlier is with respect to a background for which we know everything, maybe yes, but it has to have this problem.
No, it's clearly the statistics of the micrograph are going to look different than statistics of white noise images. That's why that's the whole basis of autocorrelation. But if you just try to do detection, you will not be able to do that. Okay, so there is this two-stage framework. The first stage, we just estimate statistics from data. Second stage, we need to solve some optimization problem, typically a nonlinear inverse problem. Okay, so again, just for illustration, so you get a sense of what's going on, let's even consider a simpler problem in 1D. Okay, so in 1D, we have a very long time series. And suppose that there is some short signal. In this case, it's this blip, okay, that appears multiple times in the time series, but you don't know where. Okay, so suppose it's like radar, okay? So someone is using radar to estimate, to detect objects in the sky, but you're just a listener, okay? And you don't know what was the template that was being used, but you hear multiple reflections, multiple noisy reflections, and now perhaps you can now figure out what was the template that was used, okay? So you get all those noisy reflections at different delays, but there is so much noise that you cannot see anything. So this would be the picture on the right. But the picture on the left, okay, we can all just see it with our eyes. Picture in the middle, again, we can all see it with our eyes, but we'll get better estimation by just averaging. Picture on the right, nobody can do detection. But again, you can estimate the underlying signal by autocorrelation analysis. Okay, so you can. But now, if we just stop at autocorrelations of order 2, it will not be sufficient. And the reason being that phase retrieval in one dimension has no unique solution. Okay, so we need to go to autocorrelations of degree 3, basically to the triple correlation function. And from the triple correlation, we can now get the phases. So, and what I show you here are two pictures, basically that the purpose is to compare autocorrelation analysis with maybe a much more classical maximum likelihood expectation maximization framework. Okay, so in the expectation maximization, I just chop my very long time series into many, many, many pieces. And for each piece, I can now say, like, okay, what's the probability that the signal appears in with shift 0, shift 1, shift 2, and so on. And just marginalize over it, and now do many, many iterations until convergence. So what you see on the left is that the root mean squared error of both methods, like both EM, expectation maximization, and autocorrelation analysis, is more or less the same. You get more or less the same errors. EM is doing slightly better, but not significantly. And what is interesting is the behavior as you change the noise level from very low level of noise, where the slope is 1, to very high level of noise, where the slope is 3. Why do we get slope 1 at high SNR? Because then you're in the classical statistical estimation regime, okay? You're basically here, okay? So we know that the quality of the estimator will improve as a sigma squared over n, okay? That's the usual over t, if you think of t as the length of the time series. But here, or here, okay, the algorithm for autocorrelation analysis use autocorrelation of order 3. So triple correlations, basically now I'm looking at the noise variance cubed. So the effective noise variance after I multiply 3 terms is now, at high noise regime, is sigma to the 6, or sigma squared cubed. And that's why you see that the slope basically changing from 1 to 3. And interestingly, even maximum likelihood give you the same slope, okay? Now, but the main advantage of autocorrelation analysis compared to EM is the running time, okay? So because you just need to do one pass over the data, the running time is more or less constant across all noise levels, okay? Just this one pass over the data. Whereas you can see that EM starts struggling a lot at high noise levels. And the reason being that it needs more and more iterations until it can converge. So the initialization is poor. You just don't know what is the signal. And there is very weak correlation to drive you in the right direction. So you need many iterations until convergence. And you can see that the difference can be quite striking. I mean, by, say, a factor of 1,000 and even more in the running time. OK. So, and here we even do like more sophisticated scenarios where we allowed, say, 2 signals to appear arbitrarily close to each other. So you also need to include this spacing distribution between images, or between what is called sometimes, say, in physics, the pair correlation function. We call it the pair separation function. You also need to include both into the autocorrelation analysis framework and EM. OK, so this was a long introduction, okay, for autocorrelation analysis. And now I want to shift gears and talk about the application, Cryo-Electron microscopy. So as I said, it's a method for determining structures of 3-dimensional proteins, other biological molecules, and hopefully atomic cell resolution. And the way it works is actually very simple, I mean, compared to, say, NMR. Okay? So the way CryoEM works is that you basically freeze many molecules in a very similar of pore size. And at the moment of freezing, every molecule just picks some random orientation and random position within the ice layer. The ice layer is so thin that if you look at it in the vertical direction, you would see at most 1 molecule there. And basically now you shoot an electron beam perpendicular to the specimen, to the ice layer. The electron beam would go through the ice layer, would go through the molecule if there is a molecule there. And beneath you have a detector, or in the old days they used films, but now they use much more sophisticated detectors. And what it measures for you, I mean, the pixel intensities are related to the molecules, basically to first approximation, just to get your ideas right. It's basically just the tomographic projections, meaning the integral in the direction of the beaming electrons. So the molecule creates some electric potential. So this is a potential in the 3-dimensional space. And you integrate it in the direction of the beaming electrons, say in the z direction, if you wish. So you get an image of just x and y. But it's not like taking a regular photograph. It's what is called tomographic projection. OK, so this is just an artist's concept. These are not how projection images actually look like in experiment, but just for you to understand the essence of the problem. What you see on the right is, again, a synthetic micrograph, where the first step in the computational pipeline is usually what is called particle picking. So every such projection image is usually called a particle, and it corresponds to some of the real molecules here. And you just do image segmentation. You crop many particle images. Yeah, question?
I've got a question about the procedure, in fact.
Yeah.
This is immersed in a layer of water, so there are some molecules of water, and when they crystallize because they become ice,
Yeah, so they
change the
let me stop you. So they freeze it so quickly, so that what you get is what is virtuous porous ice. Okay, it's not the crystals that you have in the refrigerator. Okay,
So it doesn't change.
that was okay. We'll get later to the Nobel Prize, but one of the laureates is the guy who actually figure out how to freeze the water. Okay. Okay, so yeah, because otherwise, like Leo says, the contribution of the signal due to the wwater would be overwhelming the signals you really care about. Okay, so the reconstruction problem is somehow to figure out a way to go from the 2D projection images that are noisy, not so noisy here, but I'll show you more noisy images in a second, and with unknown orientation associated with them, and from this to predict the 3D structure. So very different information from what you get from NMR. Okay, so here just to illustrate the level of noise that we have in experimental images. So these are just a sample of 2 images out of a much larger collection of about 17,000 images. These are images from Fred Seagross at Yale. And so this is not a micrograph. This is just one particle image, okay, that was picked from the micrograph. So presumably, there is a molecule inside here. Here is another example from another collaborator, Adam Foss at UCSF. So this type of images led to a recent paper in Science. This is from a much larger sample of about 100,000 images, also much larger images, almost 500 by 500. And again, you can see that they are very, very noisy. Okay, so now CryoEM as a field has really undergo a revolution in recent years. Okay, so what you see here is a picture that try to illustrate this transformation. So from left to right is basically progression over recent years, from let's say 2012 to 2018 here. And what you see on the left is the type of resolution that you could have gotten, say, 6 or 7 years ago. And what you see on the right is the resolution that you get today. And the improvement in the quality of the map is mainly due to improvement in hardware, in particular detector technology. Okay, so I don't want to go into the specific details, but now you can get to really high resolution using CryoEM. So what you see here is a 2.2 angstrom resolution. And some reconstruction have even broken the 2 angstrom barrier. And due to those advancements, the Nobel Prize in Chemistry in 2017 was awarded for 3 of the pioneers of this method of CryoEM. So as you can see, for developing CryoEM for the high-resolution structure determination of biomolecules in solution. And this was not just recognized by an award in Stockholm, okay, but basically many universities, medical research institutions all over the world that are investing a lot in this area, okay, meaning purchasing quite expensive electron microscopes and microscope facilities and so on. And even at Princeton, where there is no medical school, there was a recent investment in a new CryoEM facility and state-of-the-art microscope. Yeah.
Resolution of NMR.
So in NMR, you can get to also to 1 to 2 angstrom resolution if you're if you are if you are doing right.
There's no resolution. Okay. For NMR structure, there's no concept of resolution.
I mean, there is a notion. I mean, what they do many reconstructions, and they define something called RMSD. Okay, that gives you an idea of how far different reconstructions are from each other. Okay, but also in CryoEM, the definition of resolution is let me say, under debate. Let me say to the very least. Okay. For those of you here that are interested in working on CryoEM data, it's actually very easy. Okay. You don't need a CryoEM machine. All you need to do is to go online. There is a public repository of EM data, okay, with lots of different data sets that you can download. The only thing is that sometimes you'll need a very large hard drive, okay, because data sets can be quite large, especially if we're talking about the new detectors. Okay, so you can see that it can be the range of, say, 10 terabytes. So the microscope produces a lot of data. So, okay, so why CryoEM? Okay, if I want to compare it to X-ray crystallography or NMR spectroscopy, so one of the main advantages of CryoEM is that it completely bypasses the bottleneck of crystallization. Okay, it's a completely general technique. You just need to freeze the molecules in water if you wish. But there is another advantage, is that because it's a single particle method, you can see individual particles. In principle, one should be able to also extract what is called conformational variability. So many proteins are not just rigid 3D objects, but they change their conformation, okay? And because each conformation will be represented in the CryoEM data set, in principle, you should be able to not just to get a 3D reconstruction, but actually to get a movie, if you wish, of all possible conformations and how they change from one conformation to the other. Whereas in NMR and say in crystallography, this is a much more complicated task because the signals that you measure come from the entire aggregate of all the molecules in the water solution, let's say in NMR, or from all the diffraction pattern correspond to all the molecules in the crystal. And even like the crystallization process itself usually prefers one conformation over another just to get the molecule to crystallize. So why now? We covered it a little bit. Okay, why us? Okay, so one thing that you need to understand is that once the experiment is done and the data was acquired and collected, from this point on, the entire reconstruction process is entirely computational. It's all about math, algorithms, statistics, image processing. Okay, there is no biochemistry, and you don't need to know physics, you don't need to know biology, you don't need to know anything, okay? So it's for the community here, I think it's a very accessible 5 minutes? Okay, good. It's a very accessible topic. And there are still, I hope I'll be able to convince you there are many opportunities for people around here. So let me show you a movie, okay, just to illustrate what are the type of things that we can do. Okay, so this was done with two of my former postdocs, Roy Lederman and Joachim Anden. So what you see are basically reconstructions that we did, and also a reconstruction of the heterogeneity at low resolution on the right. And the map on the left that you see in different colors, so it's red are not Republicans and blue are not Democrats. It's just regions where we predict there is high variability of the molecule. This is in red, and blue is the region where there is low variability. And white is just a medium variability. So I think the next molecule is my favorite one in terms of the continuous heterogeneity, so I'll show you that one as well. But you can see that there are, okay, so this is in collaboration with Ninian at Princeton. You can even see like the helices, okay? It's very nice set of data. Maybe I'll show you one more, because what you see here, the fat region, is just because it's sitting in the membrane. So that's what, what we're recovering. So here, for example, you can see two regions like moving in a synchronous fashion. OK, so I'm sorry?
What is the left and the right?
So the left, you can see it's high resolution. The right is low resolution. But the right is also showing you conformational variability. OK, so for those who really want to and really care about it, there is also a software package that we developed called Aspire. It's an open source package. You can have it in MATLAB and Python. So I have maybe 3 minutes?
Yes, exactly.
3 minutes, OK. So in 3 minutes, I'll try to give an idea how you can do autocorrelation analysis to solve CryoEM. OK? So one thing that OK, so we covered this, OK, that projection images are just path integrals of the electric potential after rotation, but we don't know the rotations. OK? So one way would be to try to estimate those rotations, and then we bring it to a classical computerized tomography problem. But at very high noise levels, OK, as we realize from all the discussion before, estimation of rotation is going to be impossible, or very, very inaccurate. OK, so let me skip that and that and that. OK, so if we cannot estimate rotations, can we still solve the problem? So the idea would be to somehow look at statistics again. OK, so with peaked particles, OK, I don't have in 2 minutes enough time to show you how you can do it directly from the micrographs, but that's something that we work on right now. With peaked particles, that was something that was proposed a long time ago by Tzvi Kam, OK, from the Weizmann Institute in Israel. And what he said, OK, let's compute statistics, OK? Just the average of all the images, the second moment, the triple, the third order moment, and so on. And why it should be possible maybe to reconstruct that, let's count how many free parameters we have in essence. Okay? So the mini image, okay, would be a two-dimensional object. It's an image, okay? But really, because every image can appear in all possible in-plane rotations, because of this, we're going to get a radially symmetric image. Okay, we're integrating over all possible in-plane rotations. So this is just a one-dimensional object. And then you look at the second order moment, okay, second moment. This should be, in principle, a four-dimensional array, but it's really a three-dimensional array. Again, because of this in-plane rotational symmetry. And then you can ask yourself, okay, so if we get from the second order moment 3D array of information, and on the other end, I want to recover a 3D object, my molecule, maybe I'm lucky enough that this is enough. Okay? And there is a way to express, only to then to figure out is how to relate the second order moment of the images with the structure. And there is a beautiful way to do it using what is called the Fourier projection slice theorem. Okay? But you can think of it, even if you don't know about slice theorem, that projections are just linear in just tomographic projections. This was the integral. So they're just linear in the 3D structure. Okay? So the moment will be some, in any moment that you like. If, let's say, second moment will be some quadratic in all the in all the voxel values, if you wish. So you see that you'll need to solve some nonlinear, in this case, second order polynomial equations. Now, in the case of uniform distribution of unidirections, the problem really falls apart in some sense. Okay, so you expand the structure in spherical harmonics. Okay, that's the right language because you have to deal with rotations over SO3. And to determine, and what you see that all these equations basically decouple. For every order of spherical harmonics, you have a different set of equations. And then you see that there is actually no uniqueness. Okay? No rigidity. Okay, you are missing for every order of spherical harmonic some orthogonal matrix. And then you have to go to, say, third order moments. But in the case of, if the distribution is non-uniform, then you can also try to solve for the distribution of viewing directions. And hopefully it will couple together all the different spherical harmonic coefficients. And that's something that we're currently developing. So this is work in progress. Also with Juha, who's sitting over there. But the principle is actually quite simple. Okay, so you take the images. Second order moment is basically computing covariance, doing principal component analysis. And from the principal component, the eigenimages and the eigenvalues, you then need to solve this polynomial system and to get a 3D structure. So you can see it's a very, I would say, simple approach for solving the problem, and a very efficient one, in the sense that it just requires one pass over the data, and it can work at any noise level, as long as particles can be picked. If particles cannot be picked, that will be a story for a different time. OK, thank you very much.
See, I think we have time for one, maybe two questions. Are there any questions? Yes.
So the pictures of Einstein show like low resolution, right? So is the limit of the resolution a limit of the method, or is this a basic equation?
So, OK. So it's a limit of computations. So basically, the larger the image here we use like 50 by 50. But let's say that you take 100 by 100, 200 by 200 images, then the computational cost associated with the inversion is polynomial, but it's steep. And so one thing that we would like to develop are more efficient algorithms for doing this inversion, especially if you go to, say, higher order moments, like third order moment.
Another question? Yes.
What's the typical size of the system for that equation? How are you solving?
So it depends exactly on the previous question. Like, what's the resolution that you're aiming? So if you aim to very low resolution, you just want to get some rough idea of how the molecule looks like, and some people call it initial model that you can use for further refinement. Then maybe there are not going to be many variables, say a few hundreds. Okay, but if you really want to go to high resolution, then it can be several thousands and even more. Okay, if you look at a molecule size, if you take a volumetric array of size 100 by 100 by 100, this is a million parameters. But obviously, we're not dealing with million parameters right now.
Okay. Very exciting. Thank you again.
Okay, thanks.